Hey guys, get started. So as you know, we had to postpone the exam last week because of the snow day. So we're going to have that exam today during the second half. So it's a shorter exam this time around. So 5 questions. So it'll just be the last after the 10-minute break. Okay. During the first half, we have to cover a new topic, which is kind of one of the last like really important topics that we have to cover, which is CNNs, basically image processing, right? So whenever you talk about machine learning, you always hear about images, and there's quite a few techniques that we can cover. So today I'll just lay out an algorithm for, essentially how to solve image type problems, right? And in this just, we still have 2 to 3 weeks left to finish up this topic and a few other things. But today I want to give this code example, given that you're going to have one last homework assignment, right? So you have one, this is going to be your last homework assignment, which will be based on images. Okay. So be on the lookout sometime this week for a homework assignment, but I can tell you already what it's going to be. It's using this code, using a technique called CNNs, which are convolutional neural networks, to train a model to classify images. Does that make sense? So that's what's left in the semester. So this assignment and of course, the term project, the neural input optimization project that you guys are working. And then, we'll have a final exam. Okay. Any questions? So you have plenty of time, right? So that's why I want to cover this topic today so that, and I'll assign the homework this week so you have enough time to do the homework and then just focus your time on the project. So obviously, images are really important. And there's quite a bit of techniques for image processing of all kinds. But the classic example of this is actually how machine learning became popular, right? So CNNs. If you really want the first like real application of machine learning, like a realistic application, was done, I think it was either the late 80s or the early 90s, going back all the way to the post office, right? So what was the problem? The problem was, you know, you have letters, right? And then you have an envelope, and in the envelopes in the US, you have zip codes, right? So what is the zip code here? 432 something. Yeah, right. So we have some kind of a 5-digit or 9-digit zip code, but it's handwritten digit, right? And so the idea was, wouldn't it be nice if somehow we can have a camera, letters are going in, we look at the zip code, and based on that zip code, the conveyor belt just sends the letter wherever they need to go. So that was the problem that they were trying to solve, and you probably heard of this person, Jean LeCun, right? So one of the godfathers of AI. So he is actually the person that worked on this project. And he's very big on CNNs. Like his whole thing is CNNs. For the longest time, up until this weekend, he was the head of AI at Meta, but he just quit to start his own startup because everyone's starting their own startup. But there's been some issues at Meta. Meta has been hiring heavily AI people, and so there were like two teams, and he was kind of like the old team, even though he's one of the greats. So he just left, right? But yeah, so that's how it is. Jean LeCun, actually, you'll be surprised to hear that he does not like large language models, and he believes that we're wasting our time with large language models. But anyway, that's it's true. Uh, but anyway, he's very famous historically for CNNs, or you associate it with them. The MNIST data set that we will use today, he created, is based on handwritten digits. It's grayscale images. Um, and so yeah, MNIST and Jean LeCun, right, very go together. Okay, so anyway, but these ideas of CNNs apply to essentially anything to do with images. Even the most powerful techniques for image processing today, which are things based on ResNets, which for those of you that take 530, you'll see that there. ResNets essentially are very complex neural networks, but they have CNNs in them. Whenever you have images involved in some way or another, the CNN is there present. Even though the algorithm may have other things, it's a fundamental technique. And so we will talk about all of those things as time permits. But for now, what I want to do is give you the code so that you can solve the homework, right? And that once I've given you that, then I'm kind of more relaxed to just get into all the different ideas. Okay, so yeah, so that's the plan for today. So image processing, we're in the third of the semester. And so if you notice, we are about, I'm recording this, we've completed, exam 1, your first neural nets, you did that homework. Cross entropy has been completed. Neural input optimization with you guys, we completed last Monday, right? And I posted the 2 videos that you should pay attention to for your project. Performance metrics, I know I covered this with you guys, at least the first half. Exam 2 has been, that we're doing today. We're doing exam 2 today. And then as you can see, all that's left in the semester is CNNs, which we're going to cover today. And then after that, things like loss functions, differentiation, all these things are more theory, so I'm not so concerned about it. We can always find a little bit of room, even in the last lecture. Unsupervised learning. And then stable diffusion, if time permits, I will cover it. I was going to give you a stable diffusion homework, but I'm going to scale it down to just a CNN homework this semester because I'm giving you that NIO project, okay? Stable diffusion is an algorithm that I'll cover in 530 as well because it's generative for transfer learning based models. All right, for processing images. All right, so anyway, so that's the plan. So we are in this module today, all right, CNNs. CNN stands for convolutional, CNN stands for convolutional neural networks, okay? As usual, so I'll talk a little bit about the homework. So a couple of things. So the code is pretty much the same that you need. But the example I'm doing, which is what I always do, the images are black and white. But for your homework assignment, your images will have to be color images. Okay? So that means RGB. And you understand how a tensor is, right? So instead of images that are just, one grid of 28 by 28, it's going to be 3 grids. So you'll have to modify the code for that. I'm also not going to give you the code on how to read images from files. Instead, I'm just going to use a library for this example, the MNIST library, but you guys will have to solve that problem when you do your assignment. So as far as the assignment, I'm just going to let you guys select your data set. This is for the homework. This will be homework 4, I think. So select a data set of images, right? And you're going to train a model to do classification on the images and and measure performance on the model. And then you'll submit it. Does that make sense as far as the homework, what you have to do? It's very easy homework, essentially just to make sure you guys can do this technique. Questions? And you'll use, obviously, the code I provided in PyTorch and so on. Oh, yeah, go ahead. What's that? Yeah. Yeah, so the example I'm doing today is MNIST. So that has 60,000 images for training, 10,000 images for testing. You will definitely need a GPU for this because it's much, much larger compared to everything we've done. The classes is 10. So it's okay if you just have 2 classes, just pick whatever data set you want. The famous ones are MNIST, which is black and white, and then Scifart 10, which is color images. But they're kind of very similar. Scifart 10 has been made to be similar to 10,000, yeah. 10 classes categories is fine, or two. I'll write this up. So I'll create a link where I'll put in all the requirements, but I'm just kind of, if you guys want to get started now, you can go ahead. And you'll see it sometime this week. Okay? Yeah. So obviously you take a machine learning class, you got to do some image processing. So we're going to do classification, but we're going to build this from scratch. It should be no surprise that 70% of the code is exactly the same. And what's going to be changing is we're going to use these new constructs called the CNN and so on. So today my goal is only to show you how to use the code. Later on, we're going to dig deeper into like the theory and things like that. Okay. If you, as an aside for you guys, even though I'm just reading directly from a library, I have posted the MNIST train and test as CSV files also here. So you can go ahead and try to load these, right? So the trick is you have to read the data and then load it into the data loaders, right? So that's the key. You got to figure that out, but I've given you plenty of examples in the previous lectures on how to do that. So you should be able to do just that, okay? So when I provide CSVs, obviously that means you don't have to use any special libraries like Torch Vision, etc. Okay, but if you're using actual images, it may be where you have to read in things as images and then take those images and convert them into actual tensors. Okay, so that's essentially the idea. Notes, hopefully you guys are reading these. So I provided here my notes on convolutional neural networks. So you can read through the whole description of it, and it walks over the code, which is the code that I'm using right now. So this will have more explanations. Okay, and finally here then we've got the code that we're going to be using today, so we can click on that. Right, and I have several code examples in here. I even have some small data sets. These are not enough for your homework, but I have this fruits data set. So certainly for your homework, you have plenty of examples here, okay, to take a look at. The ones that say SciFar, for instance, are using color images. All right, so they handle that. Today, we're just going to start with this one, MNIST CNN, which is using the famous Jean LeCun MNIST data set of handwritten digits in black and white. The other thing is, as time permits later, we'll get into the math and what convolutions are. And I have an example with an algorithm of how that works, but we'll save that for another time. All right, so given that today we're kind of limited to just the first half, since we have the exam on the second half. All right, so I think we're ready. So we can do this with Colab. So let's go ahead and load Colab. Click on Colab here. We're going to add a few cells. And because you guys understand tensor operations and everything, tensor operations will be very useful here because we're dealing with these strange shapes, right, of images that were being processed. So we need to sometimes perform some tensor operations on them, but I'll show you how to do that as well. All right, so the example we're going to do is this one, MNIST CNN. So you can click on that one. And you can see I have all the information here. It's not too long. But essentially, we're going to start with a few libraries. So definitely a few new libraries for this type of problem. The key one in PyTorch is something called Torch Vision. So Torch Vision is an extremely powerful library, and I'll briefly show you a couple of things that I like to use from Torch Vision for processing images. So you can see we're still using Torch, NumPy, but now we have Torch Vision. We have this thing called transforms from Torch Vision. This is really important because when you have images, you do transformations to these images, right? So if they're in color, you make them black and white, you reshape them, you augment them, you convert an image in a specific image format to a PyTorch tensor, things like that, and back and forth. So there's a lot of operations, and that's usually something you do with PyTorch, or sorry, with Torch Vision. Pill is the standard Python image library. So it's a very famous library for processing images in Python, and then matplotlib, which you guys are familiar with. So we're going to load the libraries. A little bit because Torch Vision is a big library. Okay, there it is. Okay, so the next one is, this is going to be a classification problem. All right, so we're going to need the metrics that we actually went over the theory of last week. Remember, if I haven't stressed this enough, the F measure is the classification metric that you should focus on. Okay, is the most important one for classification problems. Okay, and then the familiar optim and torch NN. So as you can see, at this point in the semester, we're in week 13, a lot of this code is very familiar, right? So you see that like a lot of it, you're starting to look at it as a template. And this is one where there's a bit of a deviation, but you are familiar with a lot of the construct. All right, so this is the learning rate, the number of epochs, so it's about 20 epochs. The batch size is 32 here. Remember, with images, you got to be careful with the batch size because your tensors become huge. There's an explosion in size and you can run out of memory. So for this one, you may actually later need to switch over to the GPU as we run it. Okay, so here we are. And in this example, I'm just using from data sets, the MNIST data set. As I said, just pretty simple, although we can picture some of it, but I wanted to keep this quick and also give you a challenge for the homework assignment itself, right? So you should not read your images from a library, okay? When you do your assignment, try to download some data set. Imagine that. Why would you want to do that? Because if you were doing your own project, right? Let's say you work in a factory, there's not going to be a library for the pictures of your factory, right? So you would take them and you would deal with them. Okay, so that's kind of what you want to mimic. Okay, so from data sets, we import the MNIST data set. We provide a data path so that it creates it in Colab. Notice that you specify if it's trained, if it's true or not. So if you want the trained version or the test version, and if you were going to download them every time. Okay, and then you assign it to a variable such as MNIST train. So you can see the data set is being downloaded right now, right? So the data set now should be there in data, MNIST data. Okay, this is, I just downloaded the data like that. Okay. So notice this one is the test set. So it says MNIST test data set is equal to datasets.mnist, data path, train equal false instead of train equal true. And you download the data set as well. And so now we have our data and we're just going to start processing it a little bit. So one of the things that we're going to use first is as we assign, we're going to create now not just data sets, but torch tensors, okay, of our data. And so I'm going to show you a very nice way of doing this. You can see that here. So I'll go over it. So notice I'm creating mnistrain underscore tr because that means it's going to be already in a torch tensor format, a big tensor, right? This is going to be, it could be 4-dimensional if I had RGB. Okay, so we're going to create it, use data path. It's going to be trained, so it's the same construct as before, datasets.mnist. This is going to be for the train set. We don't download it anymore because we already have it. But notice here that now it has this thing called a transform. So the transform is equal to transforms.compose. So transforms.compose is a very handy thing. Notice the transforms is coming from Torch Vision. Okay. And it's essentially like a list or a pipeline of processing steps for your data set. Do you see what I'm saying? So you have a data set, it's going to go into this pipeline, but you set up a sequence of steps that it's going to go through. Okay. So in this case, compose only has one step, which is transforms dot to tensor. But here I could have other things, like I could have, for instance, dot reshape or something like that. You see, so I could have a sequence of things that I want to do to this data. In this case, all I'm doing is converting the data from the format that it currently is in to a tensor, to an actual torch tensor. Make sense? And so you can add more things to this compose, but I'm just keeping it simple here. Okay, so now I have this as a tensor, so hopefully I can print out like shapes and things like that, and I can treat it, do operations on it. Let's repeat this process now for the test set. So test set. Oops. So if you notice, mnist test tr, datasets.mnist, data path, train false, because this is a test set, download false, because I already downloaded it. And then we have this transforms option, and we compose a pipeline, but we only apply transforms to tensor. Okay, so I run that. Okay, so now I have my data ready to go. So I can, for instance, print something. So this is going to be mnistrain tr. So this tensor over here, right? I'm going to just go ahead, grab the data, print the shape. So you can see the shape here is 60,000, 28, 28. If this was color images, it would have been 60,000, 3, 28, 28. Got it? All right, very important. Because it's one, there's no need to have a fourth dimension. All right, so here we have this. We can view an image also. So display an image. So for instance, what we do is we go to mnist test tr dot data, and we just grab image 123, whatever that is, in that sequence, convert it to NumPy, and then we invoke. Oh, give me a second. Okay. So we invoke image.image from pill. So from the pill library, we import image, and we're just going to say image.fromArray, which is a NumPy array. And now, if we run this, you can see it's a 6. All right, we can do another one. Let's do 132, and that's a 5. So these are handwritten digits, okay? It's going to be 1, 2, well, 0, 1, 2, 3, 4, 5, all the way to 9, okay? And because these, as I've explained to you guys, the whole point was the handwritten digits of the zip code in a letter. That was what they were trying to solve back in the late 80s, early 90s. All right, so now that we've done that, we can see that we have indeed the data set. We've printed out our data. Now, remember, you have to load this into a data loader just to make your life easier, okay? So we printed the shape of MNIST train. Let's now print the shape. So MNIST test tr.data.shape. So this should be 10,000 by 28 by 28. Do you guys see that? Now you can model this without CNNs, right? What would you have to do? You would have to take that image that is 28 by 28 and spaghettify it right into a one vector. What would be the size of that vector? 20. What would be the size if you took an image that is 28 by 28 and you made it into a one-dimensional vector? What would be the size of it? It's 28 by 28, right? So it's 784. And once you have 784, a vector, then you can just use a regular neural network. So the first layer would be 784, then maybe 200, then maybe 100, and so on. But as it turns out, that approach is actually not the greatest approach. First of all, CNNs are better at images, just in general. That's number one. Number two, there's actually more parameters in that approach than in CNNs. So CNNs also have some efficiency. Okay, so just be aware of it. All right. But in this example, I'm not, as an exercise for you guys, I recommend that you try to build a neural network, a normal one, spaghettify these images and measure the performance. But in this case, I'm just showing you the how to implement a CNN. So we've got the shapes essentially. Now we're going to create the data loader, which you guys are familiar with already. So we're going to do the train set first. So notice train DL. So it's a torch.utils.data.data loader, and it just takes MNIST train TR. Okay, this is going to be one of the challenges for your homework assignment, right? That I said, I'm taking this simple approach. You guys have to read the images as if you had collected them, transform them into tensors, and load them into the data loader in one of the two ways that I showed you how to do. All right, so that's one of the challenges of the assignment. The batch size is 32 in this case, as is indicated here, and shuffle is set to true. So this is something that you guys already know how to do. All right, and there we are. So we have our train DL already. Okay, the next step is to do the test DL. We already saw that we have in our test set 10,000 samples, right? We printed out that shape, it's right there. And so in this case, remember the batch size for the test set, we just set it to the whole, even 10,000 images is fine, okay? For our system, so we have test DL, torch.utils data loader, we load MNIST test TR, batch size 10,000. Okay, and there we are. So now I have my two data loaders that I need, and all I need to do now is do some the training, right? Training evaluation. There's going to be a few tricks that I'm going to show you guys for figuring out dimensions, as convolutions sometimes transform the data into shapes that you may not understand. But there's easy ways to figure it out. All right, one handy function that we've been using so far this semester is this function for printing out the metrics. This is a classification problem. So I'm just going to use my confusion matrix, precision, recall, F measure function. All right, so now let's go ahead and take a look at the architecture. So you can see here, I'm going to use this architecture. Notice we're using the exact same approach we've been using all semester. We create a class, we inherit NN, and from there we can build our architecture. So let's take a look. So we have, the class is called, in this case, classifier CNN. Okay. We inherit NN module as usual. We have our constructor def init, and then we have our def forward. If you remember, we have two ways in which we usually set up the architecture of a neural network, right? We have one where X goes in, produces an X, and then that X becomes the input to the next layer and so on, or the NN sequential, right? You guys remember, I did use NN sequential in the LLM, right? When we were doing the 6 blocks, if you remember, and it went through. I said back then, another place where I like to use NN sequential is when I'm building CNNs, because they're also very verbose and so it's easier. So in this case, I got my super init for the inherited class. Then I take a very simple approach. I just create something called self.model. I assign it an NN sequential, and then I just start laying out the layers of my neural network. Okay, so here there are essentially 4 sections that you can think of. There's going to be the first convolution, which we will talk about. Then there's going to be the second convolution. Then after that, it's just going to be a normal feed forward layer with a flattened step in between. And then it's going to be the final layer to the outputs. Okay. And so that's essentially the process. So once we instantiate self.model, or once we define it, I should say, then we're just going to, invoke it here, self.model, and we give it inputs, which is going to be the images, and it's going to give us our classes. Make sense? So this should be familiar to you, right? Now what we need to talk about is the CNN, right? So essentially, if you notice, before, we've always used linear, and here's linear, right? So these are common things. But now, if you notice, ReLUs are also common. But now, in this example, there are a few new things. We're going to have this conv2d, right? New function. We have another function called maxPool2d, okay? And then we have this function called flatten here, okay? So the way that you can think of CNN architecture is, imagine that we all know what a Rubik's Cube is, right? So imagine that your images are like a Rubik's Cube. So essentially a cube or a hypercube, okay? That cube goes into a layer and comes out as a cube or a hypercube. So it's still of big dimensions, and it keeps going. Whenever you have CNN layers, it's coming out as a cube. But once you want to give it into the feed forward layers, the linear, then you have to take that cube and flatten it, right? So it's the proper dimensions, not the batch, but the proper, those 28 by 28, etc., to fit into a normal neural network. So that's what flatten is for. All right, so the first convolution, essentially, we're going to assume that our images go in, right, into the neural network. They're going to be 28 by 28, as we saw before. So batches of 32, 28 by 28, okay? Notice we don't have to specify that anywhere in the architecture like before. That's not necessary. Instead, what you do specify here is the number of channels. What that means is black and white is 1 channel, RGB is 3 channels. Or if you had some other invention, it would be reflected like that. But essentially, this is most commonly either 1 or 3. 3 for color, 1 for black and white. This next number, 16, means the number of filters. So what that means is that you have an image, and you're going to run a filter through that image. And that filter transforms the image. So we will talk about this a little later, and I have that example I showed you. So what does that mean? In the past, believe it or not, what happened with CNNs is pretty interesting. In the past, before deep learning and all of that became very popular, people made careers, especially in image processing, of creating filters. For those of you from an electrical background, you probably heard of low pass filters, high pass filters, right? So they let some frequencies go through and other frequencies are blocked out. If you have a camera, right, you put a little filter in front of it and it blocks out a certain light, like UV light or whatever, some light, right? Could be the blue light gets filtered out. So the image which came in with blue light ends up not having blue light. You see that? That's a filter. So we can do that algorithmically as well. And we will see that a little bit later. It's pretty simple. You use math. So you know that you have a cell with numbers, you have another, little block of cells, and that's you run them, you perform operations on the numbers, like averaging all the numbers, for instance. Do you see that? So you can imagine how averaging a whole bunch of numbers makes it blurry, right? Because everything starts to look a little bit more like the same. So we'll see that essentially. But so for now to understand is we apply 16 different filters to the image. The question is, what filters? So in the past, what we would do is without CNNs is I would have to create 16 different filters. Like I had to with my head, right, come up with, oh, this is a filter for blurring the image, and this is a filter for sharpening the image. But I had to figure out the math to do that. So I would pass one filter through and create a new image. Then another filter, create another image. You see that? See, so this was the practice. But as it turns out, nowadays, what you do is because we have so much data, we just create the filters with random values in them. And then the filter with random values is passed over the image. Do you see that? What happens is obviously the filter values are equivalent to the weights in a neural network. So during training, the values of the filter are being what? Back propagated. Do you see that? And every time a filter is passed through an image to produce another image, okay, then that image is used to classify. If it's bad performance, bad filter, bad weights or values in the filter. Do you guys see that? But because, at some point, Facebook, etc., had millions and millions of images and a lot of computing power, they're just trying 16 filters with values, back propagate the values until the filters actually start get an image, process it, and produce a new image that actually helps in the classification. And then as it turns out, you would do 16, by the end of training, you would have 16 filters that somehow magically are really good at finding things and processing the images so that they can be classified correctly. All done through the power of stochastic gradient descent. Very similar to the idea of NIO, you see? But instead of going to the input, this one goes to the filters. Okay? So this is game changer. Like think about you're an image processing person. In 10 years, you've created 6 filters. Right? And now comes a neural network, and in an hour it creates 16. And they're better than yours. Do you see what I'm saying? And people have done a lot of research, and it turns out of these 16, 6 are almost like what the human had created. But the other 10, just completely non-human concepts. But the filter was able to process the images to the point where it helped a lot with classification. Do you guys get this idea? This is really important. All those image processing people lost their profession overnight. Okay? And because they were totally displaced by the power of neural networks. But it takes a lot of data and a lot of power. Is that clear, guys? Does that make sense? And I'm not exaggerating. So imagine an image. That's why I say CNNs consume a lot of memory. Think about it. A batch of 32, 3, 28 by 28 goes in. 16 filters process that image to produce 16 images. So now you have 32, 3, 28, 28, 16. Do you see the explosion of this? Right? So that's a problem. That's a problem. So what the solution to that was to add this layer called max pooling. Max pooling is the next step, which will take the image that is 28 by 28, and when you max pool it, you cut it in half. Since you're producing an image, right, you should agree that an image goes in, it's the filters process it to produce another image, right? So 28 by 28 to produce 28 by 28. But you are producing that new image from the filter and the input. So you can control it. So really, do you really need all the data? That's kind of the intuition. And so max pooling would cut the images in half so that you could address the explosiveness of creating, multiple versions of the image. So essentially think of it as the image is being cut in half. Okay? Got it? So if the image was 28 by 28 before, after max pooling is 14 by 14. And then the next pack max pool, it's 17 is what? 7 by 7, right? And so on. Any questions about that, guys? All right. Yeah, so that's it. Now, keep in mind, if you do stride of 1, then essentially the image is 28 by 28 and comes out as 28 by 28. But if you do something like stride of 2, then it will come out as 14 by 14. So essentially, it's like a max pooling. Okay? So that's why I have strides of 1 here. So I can, because I wanted to write the code like this, max pooling. There's multiple versions of this, of course. This is just like when CNNs came out, this was the only way that you could do it, right? So I'm kind of staying true to that. Padding, of course, is self-explanatory, right? If an image, if there isn't enough for the kernel, the filter, right? It'll just pad around so it can process the size. Now notice over here, there's something called kernel size. So that's you have an image and then every pixel, it's being run through a filter. And that filter is a much smaller image that you specify the size. So in this case, 5 by 5. Any questions on that, guys? Making sense? So we'll get into the theory of that a little bit more. I'll do some examples, but yeah. All right. So you specify the convolution, okay? Then you run it through a ReLU, which is, self-explanatory. You run it through a max pool, as I said, to cut it in half. And then notice over here in the second convolution, now you do conv2. Notice that this number needs to match the previous number, 16 filters. Okay, so almost like now there's 16 channels. So, and now notice here I'm saying, okay, now apply 32 filters to these images. Kernel size is 5, stride is 1, padding 1, ReLU, max pool again to cut them in half. So essentially here there's 2 convolutions. Image goes in, filters are applied to produce 16 versions. Then that tensor, remember it's still like a hypercube, goes into the next convolution. Those 16 channels go into to produce 32. And then here, at this moment in time, we still have a hypercube. Okay? This is where we're now going to pass that hypercube to a normal feed-forward layer. So the feed-forward layer needs any cube to be flattened. Okay? And so that's the thing that we need to figure out. So when we run the flatten, it's going to give us a dimension for it. In this case, I've already calculated the dimension to be 800, but I'll show you guys how you can calculate this dimension. Okay? And like I said, there's other easier ways of doing CNNs, but I like this approach because, you have to do the calculation. All right, so you can see how to get the 800 below in the last cell. So we'll cover that in a second. All right, once we do this, so imagine we have the tensor, right? It's batch, comma, whatever the dimensions are at that point. And then we are going to flatten it. So it is batch, comma, 800. And so that's why this is 800, because it takes in that batch, comma, 800 as input. And it's a feed forward, so it converts it to 512. Like we've done before. Run it through a ReLU. Then that 512 is going to be converted into what? 10, which is the 10 classes. And then we run it, it's a classification, so we run it through some softmax function on the last dimension. All right, and then that's it. Okay, so let's take a look at it, and then we'll come back and drill down to this. But are there any questions on the overall structure of setting up CNNs? So that's basically, so you can see the code is very similar, except we've got these little con2D, max pool, and we have the flatten function just before we make the transition from hypercubes to the flattened vectors. All right, so now this is done. So now comes the training loop. This one should be no surprise. You guys are probably bored of these, but that's good, right? So you know how to do it in your sleep now. So you have our training loop function, number of epochs, the model, the loss function, the optimizer, same things. Notice our 2 for loops as usual for epoch in range and epochs. So we repeat the process, give the data to the model and epochs. Then for xb comma yb in train DL, okay, we grab xb, it goes into model to produce ypred over here. I added these things, this here, in case we have, I always like to have that in case I have a problem, right? In case my code breaks here, what will I do? I'll grab xb.shape to see the shape of that tensor. And once I know the shape of that tensor, I may need to modify it somehow. So it might be, for instance, n comma 1 comma 28 comma 28. Okay. In PyTorch, by the way, PyTorch has a preferred way in which a tensor of images when using CNN should be. And it's usually n first, which is the number of the batch size, followed by the number of channels, whether 1 or 3, followed by the dimensions of the image, such as 28 by 28 for mness. And then we can reshape it if needed, squeeze it, something like that. So I provided this example, YB squeeze, right? So in case we need it. But if we don't need it, let's assume XB would go into the model, right? That's the images. What does it produce? Ypred, which is the classes, right? So one of the 10 classes. Then Ypred is compared to YB and the loss Fn. It's a classification problem, which means we're going to be using cross entropy. We've got our loss, and then guess what? The very familiar three lines of code that do all the heavy lifting. Op, zero out the gradients, loss dot backward to calculate derivatives, the slope, and then op dot step to update the weights of the model. Okay, which is essentially everything that requires grad in the model, such as the values in the filter. Right? You guys see how the convolution operation. I'm going to illustrate it by using for loops because it's more intuitive, but just keep in mind that any operation such as that can be converted into tensor multiplications. Okay, so that is implemented obviously faster. Here, we just print the loss every so iterations, and that's essentially the same approach. Okay, so once this is set up, we are going to proceed to train the model. Let me So we instantiate classifier as model. We invoke torch.optim.atom. We tie the parameters of the model, right, to the atom optimizer. We give it the learning rate, so same thing as before. Notice that our loss function is our famous cross entropy loss. And then we pass all the parameters and invoke the function training loop. Let's run this one. And this is big. So here, if you look at the training, I'm just going to run it a few iterations so that you guys can see this is, not like previous things that we've done this semester. This is more serious. You can see it's taking a while, right? So we have to switch over to a GPU. All right, so I'm gonna do that one. So now I need to change the environment, right? So runtime, change runtime type. So T4 GPU, and I have to rerun all of it, but sure. It's just real quick. Okay, there we are. All right, so we're there. So hopefully this time it'll be a little bit faster. All right, so there's the first iteration. Um, let's see how many iterations I might. It's 20. Yeah, yeah. Let's see. N epochs is, yeah, 20. So I don't have to run all of them. I'll let you guys run all of them. I'll just do fewer epochs. Yeah, so it's fairly going. This is but I'm just gonna do like 4 iterations. And then you guys at home can try this. So you can see with a GPU, um, still with a GPU, CNNs can be challenging. All right, so so here we are talking. Let's let it run a little bit. All right, so things about images that might shock you or surprise you. Okay, these images are tiny, 28 by 28, and it's still obviously taking a while. This is also not a very deep CNN, of convolutional layers, a neural network of convolutional layers. There's something called the ResNet, which is a residual network that uses a lot of convolutions. Usually they make those very deep. That's actually, where they first encountered that problem of the vanishing gradients that was solved by residuals, which we've talked about all semester, right? So that's where they actually, deep neural networks were eventually, they proved that they were better if you use residual layers. This one is taking a while with one GPU, right? And ResNets can have 50 layers of convolutions. Think about that. A ResNet 50 means 50 convolutional layers. So that's a lot. So, that's a very, a lot of RAM and a lot of memory that's being used up. Do you guys see that? But they're very powerful, right? That specific architecture, the ResNet 50 is not just like any architecture, is a very specific architecture. All right. So imagine you have 50 convolutional layers, right? So that means that it's a fairly big neural net processing images. So that gives you some limits as to the size of the images. Right? So if you thought that, well, obviously, neural networks can handle my 8K or 16K images, No, it's not like that at all, right? So there's a limit. So any image that you have, really like 8K, 4K, you'll never be able to use it directly in a neural network. Instead, what you have to do is you have to compress them, right? You'd be surprised to know that the ResNet 50, the very powerful tool used in a lot of image recognition, etc., is only 224 by 224. So the images actually are made very small. So I think any image that is 1000 by 1000, right, in relation to 224 by 224 or 28 by 28 is already too big. You'd probably have to have a very powerful computer to be able to run a ResNet 50 on something like that. By default, the standard for ResNet 50s is around 224 by 224. Think about that, right? So there are limits in what we can do today with neural networks, and that's one of the big limits, right? But as it turns out, any image that you have that's 4K or whatever, usually when you compress it to 224 by 224, you're able to do quite a bit with it. Do you guys understand that, right? The limitation. So you can't give a CNN or a ResNet huge images, right? You have to really, that's one limit in machine learning as of today. Okay, got it? And a lot in transfer learning, for instance, for those of you that take 530, for instance, you'll see all those transfer learning based ResNets and whatever that are available online for us to use, 224 by 224. So essentially, you have to take your images and compress them to those sizes. Okay? All right. Anyway, so yeah, so small images is what is processed. So imagine, right now what's popular in the news is like the Comet, right? 3i Atlas, and they have probably images that are, I don't know, 4K, and they're doing some machine learning on them. They'll have to take those images and compress them considerably. Okay. All right. So now that I have this, the model's trained. It wasn't trained for very long, so the performance may not be great. Keep that in mind, but that's fine. So let's just go ahead and take a look at the performance. And then we still need to figure out that 800 value, how to estimate it. So we did this architecture over here. We did the training loop. It trained. Now let's look at the losses actually. So the losses are looking good, right? 0.02, 0.01, 0.003, 0.008. Good losses. I like these losses. So that's encouraging. Now let's run the performance. If you remember for the performance, we take with torch no grad because we usually don't want to update the weights. From test DL, we give it X real, or we extract X real, Y real. We give X real to the trained model. It produces Y pred. Then from Y pred, we're going to use torch max to extract the indices of the more likely class, and then that preds and Y reals is provided to our function, print metrics functions, just so that we can see the performance. So this is exactly what I've done in previous classification examples, like the wine quality data set, for instance. So we run this one here, and there we are. Look at how nice that is, right? Very good, right? This is the MNIST data set and also a CNN. Okay? So if I encourage you guys to not use a CNN on this problem, take the images, spaghettify them, but everything else, you should be able to run and see what the performance is. Okay? And so you'll hopefully see the CNN is pretty good. So this is a nice confusion matrix. Remember, we want all the values on the diagonal. Notice there are some misclassifications, like there's 9 misclassifications. Here's 7, but that's because we didn't have enough training time. It would improve a little bit, although the performance is really good. If you look here, the accuracy is 0.99 and the F measure is 0.98. Now this accuracy is good because the data is balanced. It's very well balanced. Remember, when you have imbalanced data, accuracy is no longer a reliable metric, Instead, look at precision recall, but mainly rely on F1 measure. Okay, so if I look at this F1 measure at 0.98, I think the model did really, right? You'll hardly get these results like in real settings and real world problems. MNIST is a highly studied, highly academic data set. It doesn't get any better than MNIST, okay, as far as the way it's designed. Any questions? All right. So yeah, so this is what you have to do for your homework assignment. Obviously, you're going to be using color images, and you shouldn't use libraries to get the data. Instead, you download some data set with actual images, read them from there, and so that's the challenge, right? Now, there's a few more things that we're going to explore here, but we're essentially done. So we printed out this. Now, the next thing is you want maybe to figure out the convolutional maths for your model, okay? So this is, for instance, in this example that I did, after flattening, I needed to know what this value is. Do you guys see that? But this is something that you can figure out by using just shapes, printing out the shapes, and so on. So let's take a look here. So what can we do? Yeah, so we have time. So let's go through these just to kind of get more familiar with the convolution operation, see what it's doing. So remember, I've been referring to this as a Rubik's cube, right? Going through all the layers. So it's kind of like this. We have some kind of a, this tensor of 3D, 4D, and we're going to perform operations on it. And let's just see what happens, right? Let's get a feel for it. All right, so I'm going to also, in this example, use batches of 1. All right, so obviously by getting the results, I concluded the CNN algorithm or code. Now we're just going to play with some shapes. All right, so I'm going to use batch of 1. And I'm going to create, we're going back to tensor operations. I'm just going to create random data, right? Just to see what happens when I perform the operations. So I create a torch tensor size 1, 1, 28, 28. Okay? Right? And I'm going to print the shapes of it. And you can see it's 1, 1, 28, 28. Remember, this is what PyTorch wants for CNNs. If you don't do it like this, it's going to complain about it, right? So it wants this to be the channel, essentially. All right, so I've done that. I've got my tensor. Now I'm going to apply to it some convolutions, right? And there's several types of convolutions. This is just one. So I'm going to do, if you guys remember, the nn.conv2d mat. So this is convolution 1. So it's a 1, 16, kernel size 5, stride, in this case, stride 2. All right, so I'm going to run my tensor, this one, my tensor test into it, and then we're going to print out the shape. So as you can see, what happened here is, because of the stride, it produced something like 1, 16, right? So now I ran this image. Do you guys see that? This image into this function to apply a convolution, essentially. So notice that it's now, the Rubik's Cube is no longer 1, 1, 28, but it is now 1, 16, 12, 12. The 12, 12 is because it was cut in half by the stride, and the 16 is because there are 16 versions of the original image because there were 16 filters. Yeah, you don't get that value? Because it probably did some padding. It's the stride here. So that's what I'm saying. It's like See, there's this 24 by 24. So it's what it does. It depends on the function. It's not exact math in what I was saying. That's right. There's 16 images. Yes, exactly. It's what I was saying. Before, think about it in your mind. You had 1, comma 1, comma, so you just had 28 by 28. Yes? Now, that was not even a cube, right? That was just a grid. Now you have, ignore the 1 here because there's nothing. You have that 16 times. But it's, I'm not using the max pooling, right? So it's very close to the original value of 28 by 28, but by doing stride 2, it's like I have the max pooling. It's essentially just cutting it in half, and you can see it does 12 by 12. Remember that it's converting the original tensor into something else via the matrix multiplications, exactly what we've done before, right? Like from one vector space to another vector space. You guys remember that, right? But it's the values that are produced here depend on the values in the filter. Okay, and those are the things that are learned via backpropagation. Got it? All right, good. So yeah, I'm just playing with it here. Just doing operations, okay? So I did that. Okay. I can do another one. So this is equivalent to having that second convolution, right? So conv2d, notice I had 16 outputs. So now my input is 16 to produce 32 with a kernel size of 5 and a stride of 2, like max pooling again, right? And that, what goes in here? Res conv1, right? So the previous tensor now goes into this operation. So you see, now I have 32, but they are 4 by 4. Do you guys see that? So they've been cut in half. Remember that these things are getting padded, right? So that is probably accounting for that discrepancy so that the filter can run. So here, if I do 1, it should be big closer to 12. So it's 8, comma 8. All right? So that, let's leave it at 2. Okay. Then I have, a final one, a view. And what is this one equivalent to? Flatten. Remember that I talked about flatten? So here I have 31, comma 32, comma 4, comma 4. But I have to flatten, right? So the way that you can do it sometimes is you just leave n batches. That's the fixed number. And then when you use -1, you're just saying convert this thing of size 4 into just of size 2 because there's 1 and 2, but convert all the other dimensions into whatever it is without losing data. So that's why it comes out to 512 over here. Does this make sense? So this should be what, 16 times 32? Is that 512? Yeah? Yeah. Got it, guys? So no data is lost. It's just a flattening operation. Okay? So 1 comma 512. So that Rubik's Cube has been flattened now into some kind of a vector. All right. Now this one is conv2d with max pool. Okay. So we can try this one out. So that's going to be large math model. More like what we did. So I'm using an NN sequential. Notice this one is color images 3, right? You see the RGB channel is 3. 16 filters, kernel size is 5, stride of 2. There is a max pool as well. And there's a whole bunch of ReLUs and so on. And then here, this is 16, so this has to match over here. That produces 32. Max pool, so this is essentially the whole neural network. It takes in a tensor as input and produces something after a lot of processing. So let's see what that looks like. I'm going to do batches of 10 here just to illustrate this further. Okay, so I'm going to create a tensor randomly, n batches. So this is going to be 10, comma 3, comma 256 by 256. Pretty large tensor, this one, because it's color. This would be actually probably bigger than what ResNet wants to handle, right? So you better have an A100 for this for this one. Okay, so you have large my tensor test goes into large maths model, right? And it's just gonna process it, and notice it comes out as 10, comma 32, 15 by 15. Do you guys see that? So notice it's funneling, right? The tensors as it starts producing new versions of it. Any questions? Make sense? Okay, good. So this, in this example, so I'm just really showing you the behavior, what the CNN is doing. So there's no mystery. We can use the view again and use the little -1 index, which is to flatten it. So notice I just have 10, 10, but I'm going to flatten the rest, right? So this whole thing is going to be flattened. And now it is 10, comma 7,200. Do you see why it's important to flatten? Imagine in that, we always have in a CNN, right, a feed-forward layer in the end. If you notice, the LLMs had also a feed-forward layer in the end. I don't know if you guys noticed that before the classes. But notice that even though this seems like we flattened it or we like made the tensors quite small, still look at how massive this is. This is pretty big. 7,200 is really big. Okay? So that's one of the issues with CNNs. Okay, let's do one more example and then we'll wrap up. A couple more examples. So let's do this one. This one is pretty similar. Convolution, second convolution. Okay. Batch size n batches is 10. That's the same as before. I'm going to create a tensor, this time not color. Notice it's 1, comma 28 by 28. I'm going to run this through maths model, right, and print the shape. And notice it is 10 by 32, 4 by 4. Okay, 10 by 32, 4 by 4. That's what it comes out to. So instead of that, I don't like, I'm pretty sure there's, in fact, some formulas that you can learn and memorize to figure out always like what these dimensions are. At some point, I just decided I like this method better, right? So I always just print it like this, just to figure out if I have any questions on what's going on. And then I've shown you that we can flatten it. Finally, for this example, for this problem, this is the one we did. We'll wrap up with this. This was the actual architecture that I was using for this MNIST data set. I had convolution 1, convolution 2, and then I had my flatten function. That's how I was able to figure out the value 800, okay, that I had to hard code. So just do this. So essentially, I take the tensor up to that point so I can print out the shape. Whoops. So now I'm going to go over here. I grab from my actual data so that also I can be consistent there. So from my train DL, I just wanted to print out the shape. You can see it's 32, comma 1, comma 28 by 28. So now I run it through that. I'm going to create a random tensor of that size. So n batches by 1 by 28 by 28, run it through model RC, which is this one, and print out the shape. And you can see there that it is in fact 10, comma 800. So this 800 is the 800 that I hard coded right there that I needed to figure out. Got it? This is one way, as I said, of doing CNNs. There are other ways. I leave it to you guys to try this one or other ways. Remember your homework, which I will be posting sometime this week, should be with color images. And yeah, that's it. Any questions? All right, so today, it's 6:19, so it's almost 6:20. So we used up the first half of today to introduce code for CNN. So now you have in your Arsenal toolbox, right, a new technique when you're dealing with images. And you will have a homework assignment. This is kind of like the last main topic of this course, to be honest. And what we have left is really just drilling down into things like that's what we're going to be doing next week. Next week, you guys have class, although it's Thanksgiving week. We do meet on Monday, so we'll cover that. And then the following week is the last lecture, because after that is presentations and final exam. Everyone with me? Any questions about anything? All right, so that's it for this lecture on CNNs. So I'm going to end this video here.